The title of my talk looks very philosophically, and indeed it is related to philosophy. Why? Because there was a great Polish philosopher, Leszek Kołakowski, who frequently repeated a statement that the greatest problem in philosophy is to prove the necessity of the existence of the universe. This is crucial, that it is the necessity, not the first one. Of course, we know that the universe exists, but to prove that it must exist. Because both religions and science, as we understand it now, claim that the universe is in some sense contingent. Of course, this philosophical problem is not solved in my opinion, it will not be solved soon. It is an eternal problem. But I relate to it because physics, I will be talking about physics, and physics makes an interesting contribution to this problem. Namely, the physics, modern physics, puts forward the question why the space-time is not empty, why there is matter. Because the universe is both space-time and matter, but in principle it could consist only of the space-time. Why it is filled with matter which we observe and which is the constituent of our bodies. So without matter, obviously we would not exist. And this problem, why there is matter at all, is generated by modern quantum physics. Because according to quantum physics, there is exact symmetry between matter and antimatter. So antimatter should also exist. So first the question is purely observational. Do there exist considerable amounts of antimatter in the universe? The problem is with recognizing it is that antimatter has exactly the same properties. This is the meaning of symmetry. It has exactly the same properties as matter. So looking at some body, we are unable to state whether it is made of matter or antimatter. And of course, getting into direct touch with antimatter is rather dangerous because then there is annihilation, as you well know. So what we can do, first, we can make observations, and there are two kinds of observation. We register cosmic rays. They are these ultra-relativistic particles. These cosmic rays are dominated by protons plus a small amount of electrons, but it's interesting, protons and antiprotons. And observations say that the ratio of the number of antiprotons to protons is about 10 to minus 4. However, this result does not mean that there is in the Milky Way or in its direct vicinity, there is a large amount of antimatter which is the source of these antiprotons. These antiprotons which we register at the Earth usually come from pair productions. Namely, we have a collision of two ultra-relativistic protons, and during this collision there's produced pair proton-antiproton, so we obtain 3 protons and 1 antiproton. So we observationally say that there is no primordial matter in the galaxy. The second kind of observations is such that that we can assume that galaxies rather far from our Milky Way are made of antimatter. Then we assume that there is a border between galaxies and anti-galaxies. On this border there should be contact of particles and antiparticles leading to annihilation, and we should observe gamma radiation coming from this annihilation, and also this radiation should distort the spectrum of cosmic microwave background radiation. However, nothing similar to this effect is not observed, and the conclusion is that the observable universe must consist of matter without macroscopic amounts of antimatter up to, say, Hubble radius c/h0. This is to some extent, the size of the observable universe. There is, however, one more possibility, that very, very distant galaxies which are beyond observation, that they may be made or contain antimatter. However, this possibility is excluded by modern cosmology, because cosmology claims that in the history of our universe there was the period called early or very early universe, and this very early universe was filled with plasma of hot particles and antiparticles. Well, so if we have such a hot and dense, must be both hot and very hot, means high energetic, and dense plasma, there are intensive interactions, electromagnetic, strong and weak interactions, and there's permanent production and annihilation of pairs. For instance, we have the most important reactions are written here. We have positron plus ordinary electron called negatron. They annihilate into 2 photons, 2 gamma, or in the opposite direction, interaction of two photons produces this pair. And similarly, we have a pair of proton-antiproton, which may annihilate or be created by 2 photons. And first, we don't know any physical mechanism which could separate particles from antiparticles. Assume that we have a mixed plasma of particles and antiparticles, and we don't know, there's no mechanism, not only we don't know, but it is claimed that there's no mechanism which would separate these 2 components, spatially separate, so that we could get parts of the universe filled with matter and other parts filled with antimatter. What is more is that even if such mechanism would exist, then it would be inefficient. Because if we have hot ultra-relativistic plasma, even if we divide it into matter and antimatter, interactions of particles and similar interactions of antiparticles immediately produce pairs, particle-antiparticle. So if we make such a separation unknown way. So this mixture of particles and antiparticles will be very quickly restored. So this means that that in the early universe we had plasma of matter and antimatter. What is most important are pairs, electrons and proton pairs. And when the plasma cools down due to the expansion of the universe, these pairs annihilate at low energies. New pairs are not created, so matter and antimatter disappear. So, from this, I enter into detail of this concept, namely, because we have this matter-antimatter symmetry in properties, then it seems quite reasonable to assume that in the early universe, the quantities of particles and antiparticles should be equal. Then, if the amounts are exactly equal, then all pairs annihilate, and what remains is just background of gamma rays, and after some time we get just cosmic background radiation, which mainly consists of photons which were generated in annihilation processes. So this is the baryon. This is the problem of the baryon asymmetry of the unit. And we ask, why, assuming that we use quantum physics according to which matter and antimatter are symmetry, how can we get the universe with matter and practically without antimatter? The first conjecture that this asymmetry, baryon asymmetry, was built in the initial condition of the universe, that the universe was created in the Big Bang with this asymmetry. In fact, this conjecture explains nothing. Just claiming these are initial conditions, this explains nothing. Moreover, as I will tell you in a few minutes, this even such situation did exist, it does not explain why there is this asymmetry today. So the problem is how to explain baryon asymmetry if matter and antimatter are symmetric. Well, I start with a reminder what are baryons, because I will frequently use this term. By baryons we mean strongly interacting elementary particles. Strong means strong nuclear forces, and these particles we call them elementary particles, but in fact these are composite particles which consist of three quarks. And the latest baryons are nucleons, and they are crucial for cosmology. And these are protons and neutrons. Here you see the constituents of proton and neutron. These are quarks U and D. And in the brackets here, it is written the electric charge of each quark in units of electron charge. Electron charge is -1, and U has plus 2/3, and D has minus 1/3. So in this, adding these charges, we get that proton has charge +1 and the neutron is neutral. And as a starting point, we assume the standard model, standard particle model. In fact, in physics we have two standard models. Standard model in particle physics and standard model in cosmology. But the particle physicists prefer to just say standard model, and it means that it concerns particles. Okay. So, the standard model describes all elementary particles. You know, there are hundreds of them, but the model of all these elementary particles are made of fundamental particles, and these fundamental particles, which are really elementary, not only from the name, but according to our knowledge, they are really fundamental. These are 6 quarks called up, down, strange, charm, top and bottom. Then we have 6 leptons. Leptons means lighter particles, and do not interact strongly. These are electron, muon, and tau, and 3 new types of neutrinos, which are related to the first 3 particles. So we have electron, neutrino, muon, neutrino, and tau neutrino. So these are fundamental particles. They are fermions, so they spin. Quantum spin is 1/2. Moreover, we have particles which carry interactions. So we have 8 gluons, which we have 8 gluons which carry strong forces, and we have, because we have 2 other interactions called electromagnetic and weak forces, and they are carried by so-called intermediate bosons, W plus minus, Z0, E of course, the photon gamma. Moreover, there is very mysterious particles called Higgs particles, which play fundamental role for that standard model. So, this is the starting point, and if we try to obtain baryogenesis in the early universe, produce excess of baryons above antibaryons, we must apply, in fact, the whole very sophisticated and advanced apparatus of theoretical physics. So first, we must use quantum field theory, which is the basis of the standard model. Moreover, it must be not the standard, not the ordinary quantum field theory, but it is called quantum field theory in finite temperatures. Then we must use the concept of symmetry breaking. Then we take phase transitions taken from statistical physics. They are also applied to fundamental interactions. Of course, general relativity with its part called inflationary matters. And it turns out that this is not sufficient. In fact, we must make some extensions of the standard model. And this is the main difficulty. So, first, how large is the baryon asymmetry which must be accounted for? This is expressed in I think, one of the most important parameters which are inherent to our universe. It is the parameter traditionally denoted by eta. It is the ratio of the number density of baryons observed today to number density of photons of the cosmic microwave background radiation. This NB with a capital B, this number density of baryons, is in fact the difference between number of baryons and number of antibaryons. Well, what is important, this parameter eta is important because it is constant. Namely, these quantities which define it evolve at the same rate. Of course, the particle and antiparticle number densities evolve as this cosmic scale factor r to -3, and the number of thermal photons is proportional to t to a third power, because there is a relation that t times r is constant, so this number of photons also behaves as r to -3, so their ratio is constant. So this quantity is constant throughout, practically constant throughout the whole history of the universe. Now, what is this number? So we use, of course, the number of photons, and gamma is known very well, one of the most precise numbers in cosmology, not the most precise. And we need the number of baryons. It may be determined by three methods. One is the observations of the microwave background radiation. The Planck satellite 9 years ago gave the parameter omega b equal about 500, and the other independent method is to use primordial nucleosynthesis. The abundances of both helium-3, deuterium, and lithium-3 are very sensitive to parameter omega, so from their observed quantities we can read the omega, and again we get the same number. Omega b is 500. So if we take these two quantities into account, we get that eta is about 6 times 10 to -10. And this number, accounting for the baryon asymmetry, means that we should account for this number. Well, is it possible to obtain this number, this asymmetry, using the standard particle model, which has this advantage that it is very well confirmed by all experiments? There's no experiment or effect that would be in conflict with standard model. The problem is that the standard model cannot do it. Why? Assume that, as it seems to be most sensible, that initially the universe has eta equals 0 in the primordial plasma, so what means that the amount of matter, and by matter and antimatter I mean protons and antiprotons, that the numbers are exactly equal. Then we obtain this unpleasant effect that at low temperatures all pairs annihilate and nothing remains. No particle. But in fact, if we look at this process, of course, annihilation requires that the plasma is sufficiently dense that protons and antiprotons can meet. It may be computed when the primordial plasma was so diluted that annihilations stopped. There was no, of course, the creation of pairs, but also annihilation of pairs stopped because it was too rare. It is found that it occurs about when the temperature of the plasma is about 20 MeV. Then it may be computed in this standard model the amounts of protons and antiprotons. These quantities from the assumptions are equal, and in fact we get that the number density of baryons to number of photons is about 10 to minus 18. And this is by 8 orders of magnitude smaller than eta. So without trying to say how antibaryons disappear, we see that standard model cannot provide any explanation of the baryon asymmetry. So this means that we must use some extension of standard model, and these extensions go in all possible imaginable directions. The literature is very large. Concepts, there are a lot of concepts, but the main groups of investigation concern either supersymmetric standard model or so-called grand unified terms. Supersymmetric models mean that there's a hypothetical symmetry between fermions and bosons, so it means that each particle you observe has its supersymmetric particle with the different spin. For instance, electron, which is fermion, has spin 1/2, has a supersymmetric particle called selectron, which has a spin 1, and so on. This is a beautiful idea which appeared in the early 70s, but up to now we see no signs of supersymmetry. And there are a lot of models of supersymmetry, and most of them were excluded by other observational effects. So this is now. It is interesting to understand too, the problem is that we have two important quantum numbers, so-called baryon number and lepton number. Baryon number is +1 for baryons and -1 from antibaryons, and similarly lepton number is +1 for leptons and -1 for antileptons. These two quantum numbers, they are not related to a kind of interaction like, for instance, an electric charge, but they just express the observational fact that some reactions with particles do not exist. For instance, most of baryons are unstable and they decay to lighter particles. First, take neutron, and neutron cannot decay in a process where conservation of energy, spin, and charge, but the baryon number is not preserved. For instance, we have such decay as neutron decays into positron, negatron, and photon. It is forbidden because on the left we have baryon number of neutron is 1, while on the right side none of these particles have baryon number different from 0. So this reaction is forbidden. Proton is the latest baryon, so it must be stable. It must be stable because there is no later baryon in which proton could decay. So the correct decay is, as it is written here, neutron, free neutron, not in a nucleus, but a free neutron, decays into proton, electron plus well, it seems that there is a mistake here. Yeah, it should be anti-neutron electron. Well, so we see here we have baryon number is preserved because neutron and proton have the same value +1. Lepton number is L equals 0 for neutron, and it is 0. It is -1 for positron and +1 for neutrino. So they are so these two numbers are preserved, but there is also further numbers called electron number, which, as it is written, is not incorrect. But it doesn't. For our problem, it does not is not important. Okay. So we have these two quantum numbers, baryon number, lepton number, which must be preserved according to experimental physics. So we have no explanation why these two numbers are preserved. It comes just from experiment. Well, and these two numbers are important because what are the necessary conditions for generating baryon asymmetry? This was given in 1967 by Andrei Sakharov. The name well known because it was the Russian constructor of, first he was a constructor of the hydrogen bomb, and then he was a very famous dissident. And in physics, he put in 67, he presented three criteria which any particle theory must satisfy to produce baryon asymmetry. It was 67, it was just after the discovery of CMB. Cosmology started a serious theory in physics. It was clear that there was an early universe with plasma and hot plasma, and the problem of baryon asymmetry became clear and important. So Sakharov claimed that there must be three conditions satisfied. First, we must have baryon number violation. It is rather obvious because if we start from the initial state, the universe with eta equals 0, means the numbers of baryons and antibaryons are equal, then we cannot produce the excess of protons over antiprotons without violating the baryon number. This is obvious. The second condition says that it is in quantum field theory that there is a so-called charge conjugation. Charge conjugation it concerns so-called Lagrangian in the quantum field theory. This Lagrangian should have a charge conjugation should contain parity conjugation, means the difference between left-handed and right-handed, and both is symmetry, C and P and their together joint symmetry CP must be violated. And the third condition is that it is assumed that the primordial plasma was in thermal equilibrium, and to produce the excess we must have a short period when this thermodynamic equilibrium was broken. And this is generally accepted that these three conditions must be satisfied. So, the problem is it possible to satisfy these three conditions in the real universe? Of course, it depends on the physical theory which we use to describe the reality, it means the early universe. And this is the problem, this is called in French embarras de richesse. So this means that we have a large number of various theories which better or worse can provide baryon asymmetry, but all these theories are difficult to verify. Some of them are excluded. There are almost no positive effects. Rather, most of these theories are excluded by some experiments, but still the number of theories various theories which survive up to now is quite large. So, to see what is the problem and when possibly the asymmetry might be generated, we must look at the history of the early universe. So I will discuss for 10 or more minutes about the history of the very early universe. Of course, it is interesting in its own. So, the epochs, or sometimes it's called eras of early universe. Here I assume that the history is the most traditional. So this is the early universe as it is described by the traditional standard cosmology model, plus some extensions which seem to be unavoidable. So the first point or the first event is the Big Bang. According to Einstein's general relativity, which is a classical theory, classical in the sense not quantum theory, there was initial singularity, it's a generic effect in general relativity that a space-time contains a singularity. Space-times without singularities are rather seldom. So there was a singularity which, looking at its properties, is called initial singularity, or in astronomy we say Big Bang. We say that this singularity occurred for time equal to 0. The time t equals 0 is not only a moment, an instant of time, but it is the beginning of time and the beginning of space. So there is no point in discussing what occurred earlier, because there was no earlier. At this singularity, means at for t equals 0, all the probably infinite space observations indicate that we live in the flat space, so it is infinite. So at t equals 0, all this infinite space was shrunk to a point. It means that metrically all distances were equal to 0. In consequence, all physical quantities were either 0 or more frequently or usually were infinite, such as energies of particles, pressure of plasma, and so on. Because these quantities are infinite, and we have a singularity, it means that all physical theories which we now have are just inadequate to describe this point, because all physics which we know must occur in regular space-time. And at singularity, all physics and all scientific research breaks down. What is interesting also that the Big Bang singularity is in fact not a point. I use this term point, but it is not a point. It is just a singularity is a boundary of space-time, because space-time has 4 dimensions, so a boundary must be 3-dimensional. In the same way as if we have a straight line, it has its boundary are 2 points. If we have 2-dimensional object like a sphere, like a circle, its boundary is 1-dimensional. And if we have a 3-dimensional ball, its boundary is 2-dimensional sphere. So in this sense, also the space-time has 3-dimensional boundary, but because this boundary is singular, it is metrically a point. This means that we must say that the Big Bang occurred everywhere in space. We can't say that it occurred here and not here. It occurred everywhere. Okay, I think it's 10 o'clock. It's a good time to make 10 minutes break. So let's meet 10 past 10.
Okay, so 10 minutes break. In the meantime, you can go out, drink some water, maybe even coffee is ready, but don't crowd too much, because it's there. Maybe I can give a few very short announcements in the meantime, who's not yet registered during the big break between the lectures then.
Conservation of energy, spin and charge, but the baryon number is not preserved. For instance, we have such decay as a neutron decays into positron, negatron and photon. It is forbidden because on the left we have baryon number of neutron is 1, while on the right side none of these particles have baryon number different from 0. So this reaction is forbidden. Proton is the latest baryon, so it must be stable. It must be stable because there is no later baryon in which proton could decay. So the correct decay is, as it is written here, neutron. Free neutron, not in a nucleus, but a free neutron, decays into proton, electron plus well, it seems that there is a mistake here. it should be anti-neutrino electron. Well, so we see here we have baryon number is preserved because neutron and proton have the same value +1. Lepton number is L equals 0 for neutron, and it is 0. It is -1 for positron and +1 for neutrino. So they are so these two numbers are preserved, but there is also further numbers called electron number, which, as it is written, is not incorrect, but it doesn't. For our problem, it does not is not important. Okay, so we have these two quantum numbers, baryon number, lepton number, which must be preserved according to experimental physics. So we have no explanation why these two numbers are preserved. It comes just from experiment. Well, and these two numbers are important because what are the necessary conditions for generating baryon asymmetry? This was given in 1967 by Andrei Sakharov, the name well known because it was the Russian constructor of, first he was a constructor of the hydrogen bomb, and then he was a very famous dissident. And in physics, he put in 67, he presented three criteria which any particle theory must satisfy to produce baryon asymmetry. It was 67, it was just after the discovery of CMB. Cosmology started a serious theory in physics. It was clear that there was an early universe with plasma and hot plasma, and the problem of baryon asymmetry became clear and important. So Sakharov claimed that there must be three conditions satisfied. First, we must have baryon number violation. It is rather obvious, because if we start from the initial state, the universe with eta equals 0, means the numbers of baryons and antibaryons are equal, then we cannot produce the excess of protons over antiprotons without violating baryon number. This is obvious. The second condition says that it is in quantum field theory that there is a so-called charge conjugation. Charge conjugation it concerns so-called Lagrangian in the quantum field theory. This Lagrangian should have a charge conjugation, should contain parity conjugation, means the difference between left-handed and right-handed, and both symmetry, C and P and their together joint symmetry CP must be violated. And the third condition is that it is assumed that the primordial plasma was in thermal equilibrium, and to produce the excess we must have a short period when this thermodynamic equilibrium was broken. And this is generally accepted that these three conditions must be satisfied. So, the problem is it possible to satisfy these three conditions in the real universe? Of course, it depends on the physical theory which we use to describe the reality, it means the early universe. And this is the problem, this is called in French embarras de richesse. So this means that we have a large number of various theories which better or worse can provide baryon asymmetry, but all these theories are difficult to verify. Some of them are excluded. There are almost no positive effects. Rather, most of these theories are excluded by some experiments, but still the number of theories various theories which survive up to now is quite large. So, to see what is the problem and when possibly the asymmetry might be generated, we must look at the history of the early universe. So I will discuss for 10 or more minutes about the history of the very early universe. Of course, it is interesting in its own. So, the epochs, or sometimes it's called eras of early universe. Here I assume that the history is the most traditional. So this is the early universe as it is described by the traditional standard cosmology model, plus some extensions which seem to be unavoidable. So the first point of the first event is the Big Bang. According to Einstein's general relativity, which is a classical theory, classical in the sense not quantum theory, there was initial singularity, it's a generic effect in general relativity that a space-time contains a singularity. Space-times without singularities are rather seldom. So there was a singularity which, looking at its properties, is called initial singularity, or in astronomy we say Big Bang. We say that this singularity occurred for time equal 0. The time t equals 0 is not only a moment, an instant of time, but it is the beginning of time and beginning of space. So there is no point in discussing what occurred earlier, because there was no earlier. At this singularity, it means at for t equals 0, all the probably infinite space observations indicate that we live in the flat space, so it is infinite. So at t equals 0, all this infinite space was shrunk to a point. It means that metrically all distances were equal to 0. In consequence, all physical quantities were either 0 or more frequently or usually were infinite, such as energies of particles, pressure of plasma, and so on. Because these quantities are infinite, and the and we have a singularity, it means that all physical theories which we now have are just inadequate to describe this point, because all physics which we know must occur in regular space-time. And at singularity, all physics and all scientific research breaks down. What is interesting also that in the Big Bang singularity is in fact not a point. I use the term point, but it is not a point. It is just a singularity is a boundary of space-time, because space-time has 4 dimensions, so a boundary must be 3-dimensional. In the same way as if we have a straight line, it has its boundary are 2 points. If we have 2-dimensional object like a sphere, like a circle, its boundary is 1-dimensional. And if we have a 3-dimensional ball, its boundary is 2-dimensional sphere. So in this sense, also the space-time has a 3-dimensional boundary, but because this boundary is singular, it is metrically a point. This means that we must say that the Big Bang occurred everywhere in space. You can't say that it occurred here and not here. It occurred everywhere. Come back to the history of the very early universe. The first point of talk, not space-time point, but point of talk is the Big Bang. Now, the first epoch of this universe is usually called either Planck epoch or quantum gravity. Why? Because according to classical, classical Einstein's general relativity, very infinitesimally close to the singularity, we have regular space-time, because singularity is just the boundary of the space-time. So this means physically that if singularity at t equals 0, then for any arbitrarily small positive time t, we have a classical space-time described by Einstein's theory. It is according to the theory, but now we believe that it is unphysical, namely because if there was this singularity, this would mean that close to the singularity, both energies, pressures, and so on in matter are practically infinite. So this means that we cannot apply standard physics as we know now to this matter, and also because of these properties of matter, also space-time must be described by another term. So this close to the initial singularity, we require new physics. And it is believed that this new physics is just quantum gravity. Quantum gravity is a mysterious concept. It is interesting on its own. Quantum gravity, well, we say gravity is the universal interaction. All matter interacts gravitationally. what does not interact gravitationally is not matter. It's a very good definition of what is matter. It is something that interacts gravitationally. Because gravitation is universal, then we know that all forms of matter, corpuscular matter, are quantum. We know that interactions of particles, electromagnetic and nuclear, are quantum, so it seems unavoidable that the universal interaction, gravity, also must be quantum. This is the idea why physicists look for the theory of quantum gravity for more than 70 years. The idea is beautiful, but to construct a theory of quantum gravity, this theory is usually just called quantum gravity, it is the most difficult, the most ambitious task in the whole history of mankind. All other tasks were much easier to perform. Why? Because all the physics, all the science as we know it, must occur in space-time. Space-time which is regular up to general relativity. It was flat space-time, then we introduced curved dynamical space-time. But it is mathematically well-known concept so-called differential manifold. Well, and because according to general relativity, space-time is not a rigid stage where physics occurs, but it is space-time is also a physical object which evolves, which interacts with matter. This means that if we look for quantum gravity, we must assume that also space-time is quantized. We can quantize other fields. We can quantize electromagnetic interactions, strong and weak interactions, but these theories are just theories of quantum fields in flat space-time. And nobody knows what does it mean to quantize space-time. There are arguments showing that we cannot avoid this problem, but nobody knows how to solve it. Because we don't know what is quantum space-time, of course, we cannot say whether adequate mathematical concept already exists, or we should first ask mathematicians to introduce new concepts. So, the difficulty here is such that we have no observational or experimental effects of quantum gravity. When quantum mechanics was constructed in the 20s of the last century, it is a very surprising, very counterintuitive theory, but all its concepts were based on experiment. There were lots of experiments, and the effects of these results of these experiments suggested how to describe it. So, so the quantum mechanics was constructed in a very close relationship to observation. In the case of quantum gravity, we see no effects which we could say that they are quantum effects. According to this means that the gravitational field must be very, very strong, and we cannot produce such strong fields. And in fact, these conditions for quantum gravity may occur only, as far as we know, in two cases. The first case is near the singularity of a black hole, not on the horizon, but in the just close to the singularity of black hole, but we can't see it because it is hidden by the event horizon, or it occurred just after the singularity, the initial singularity of the universe. And this is also cannot be observed. So we believe that the first era was the era when quantum gravity dominated, but we don't know what it was. So to describe this quantum gravity, we introduce so-called Planck scale or Planck units. These are units which are constructed from three fundamental constants of physics: light velocity c, Planck constant h because matter is quantum, and gravitational constant g because there is gravitational interaction. From these three quantities we can construct any dimensional quantity. And for instance, we can construct so-called Planck time, which is 5 times 10 to minus 44 second, and the Planck length, which is 10 to minus 33 centimeters. And it is seen that these quantities, Planck time, length, temperature, density, mass, density, and so on, are either very, very small or very, very large. So this scale does not apply to our universe as we see it, but it should be the scale of effects in quantum gravity. Therefore, because we expect that such quantities as shown here were valid in the very early universe, so we claim that this was the first epoch, was epoch of quantum gravity. This first bit. So we have no theory, but even it is very difficult to describe what might occur in this epoch because at this epoch there was no classical space-time. So it means that there was no time and no space. Of course, if we have a history, whether of a state or a history of the universe, it means that the history is an ordering of events in time. We order events in time. If there is no time, we cannot order these events, and we don't know how to describe such a situation. So, what we can only say that, assuming that the quantum gravity epoch existed, that it ended. We cannot say that it ended at some time because there was no time. We can only say that this effect of quantum gravity disappeared and classical space-time appeared, but not in time order, but something like a logical order as we use logic derivation in mathematics without time. So, traditionally, we assume that there was an end of quantum gravity epoch, and we assign to this end time equal about 10 Planck times 10 to minus 42 seconds. So this is by convention, because I stressed that in Planck epoch there was no time. But we say that initial singularity was at t equals 0, and the Planck epoch lasted this period. What I say here, it is the most traditional approach to the problem. Because now it is very fashionable in cosmology to consider far more radical concepts, according to which there was no singularity, so that the history of the universe sufficiently early was completely different from what is shown in general relativity, so that general relativity is maybe restricted and so on. So there are a great variety of ideas, including also the cosmological models where we can come back in time to minus infinity. Because all these theories are untestable at present. So, after this quantum gravity epoch appears second epoch called grand unification epoch. It is claimed by some authors that it started at 10 to minus 42, the end of quantum gravity, to 10 to minus 34 seconds. However, both numbers are strongly model dependent. So, what occurred? At the beginning, this epoch, or we know that quantum gravity effects fade away and classical space-time emerges. And this emergence of classical space-time is sometimes called a kind of phase transition. I use the concept of phase transition. You know, phase transition, typical phase transition is a condensation of vapor into liquid water. And this phase transition caused that gravitation, from now on described by Einstein's general relativity, was separate from other three interactions. So, in this epoch, the description of this epoch is based on a kind of conjecture that the three other fundamental interactions, electromagnetic, weak and strong, were unified into one force called electronuclear force, and this force was described by so-called grand unified theories. The name is quite clear because we have, in physics, we have a sequence of unifications of various forces, like unification of magnetism and electricity into electromagnetism. So, we have grand unification of these three interactions. In quantum epochs, it was all interactions were described by quantum gravity. Now, gravitation is separated from that. The problem is that this beautiful name, grand unified theories, but we don't have a reliable form of this theory. There's in fact a lot of such theories appear under this name, because it is some years ago it was introduced the concept of physics horizon. The physics horizon acts like an ordinary geographical horizon or event horizon in black holes. It separates all physical effects and physical theories describing these effects into two parts. Above the horizon, there are effects which we observe in the laboratories or cosmology or astronomically, and these effects, because are observable, can be described by theories which we can verify. On the other hand, we have what occurs under the physics horizon are effects which we do not observe. We try to describe them by various theories, but we have no way to verify this theory. So this grand unification epoch is beyond or under the physics horizon. So in fact we know very little what occurred there. What does it mean? It means that we have in this grand unification epoch some matter. We have matter, and we call this matter primordial matter because it emerged from quantum gravity epoch. And we can either assume that this primordial matter had the same properties as ordinary matter, today matter, which we know well, or it might have completely different properties in this because this matter was in extreme physical conditions. So these properties might be completely different from properties of known matter. So this is important concept. Then, at the end of grand unification epoch, there was a second transition. The first phase was the separation of gravity from the other three forces. Now we have a second phase transition, namely this electronuclear force unifying the three interactions was broken into two separate theories, namely theories which we already know, this quantum chromodynamics, which describes strong nuclear forces, and the so-called electroweak theory of Weinberg-Salm model from its authors. And this is interaction which unifies electromagnetic forces and the weak forces. And it is estimated that this occurred when typical particle energy was about 10 to 15, below 10 to 15 GeV. Now, either it is unclear, according to different authors say different things. According to some authors, at the end of grand unification era, or after it, occurred so-called inflation. It is second mysterious effect occurring in the history. Namely, it may occur from 10 to minus 34 seconds to 10 to minus 32 seconds. These numbers are very strongly model dependent. So this period was extremely short. Nevertheless, if it took place, it was very deep. It is claimed that either from this breaking grand unification theories, or from other reasons, apart from the matter which we claim that we know, there were some other things. Among them, there was so-called inflation. It is impossible to identify it with any known physical field. It must be independent field. And this inflaton field had a constant energy density. This is very strange because when the space expands, we have already general relativity, and the universe expands, space expands, so all physical quantities like energy density, particle number density, and so on decrease. But this field, this inflaton field, has a constant energy density. It means that at some moment, energy density of matter, corpuscular matter, whatever it was, is smaller than this constant inflaton energy density. From this moment, the main contribution to the energy density which drives the evolution, expansion, is constant inflaton energy. And it causes very fast evolution. So, I remind you also that if we have ordinary but ultra-relativistic plasma of particles with pressure which is 1/3 of energy density, then the cosmic scale factor, we are already in Friedman, Lemaitre, Robertson, Walker space-time of standard cosmology. So this cosmic scale factor grows very slowly, namely like square root of time. But if the energy density is constant, then this universe expands very quickly. It is exponential evolution with the Hubble constant, which in this case is really constant. It is really constant, that it is proportional to square root of this constant energy. Because this constant energy density of inflaton was large, so this Hubble constant is very large, is 50 or more orders of magnitude larger than the Hubble constant today. So the universe expanded very quickly. So in this very short period, it may be claimed that the scale factor grows 10 to 30 times or more. It is possible to compare it if there was a distance of nucleus size 10 to minus 13 centimeter. After the inflation, it was distance about 1 light year. This means that because the space was expanded in such amount, such great amount, this means that each co-moving volume grows as the cube of the scale factor, increased, say, 10 to 90 times. So this means that this primordial matter was diluted to unobservable amounts. So in fact we don't know, so we cannot observe now this is primordial matter, because even it exists, that was not converted due to later interactions, then we would say that there is one electron in the volume of the solar system or larger. So this primordial matter practically disappears, and this means that we can say that it might have any properties because now they are irrelevant. So this means that the matter which we observe, and also the antimatter which partially annihilated with it, were produced as a secondary matter. How it occurs. This inflationary epoch, this expansion driven by inflaton field, must have ended at some moment. Otherwise, there would be no universe as we see. So it must have ended. Why it ended is unclear, but it must have ended. And it is claimed that the energy of this field, this huge energy of this inflaton field, now in very large space, greatly increased, that this energy was, that this field decays and its energy is turned into ordinary matter. And this ordinary matter we call it secondary matter, which was created due to inflation, after the inflation, and this is the matter which we observe now. So, one comment about it is that whether the problem is whether inflationary evolution took place or not. The idea of inflation comes from quantum field theory. There are very generic argument that something like this should occur. The problem is such that the quantum field theory is used far beyond the realm of applicability of quantum field theory, because all these quantum theories are constructed and checked in flat space-time. While here we have space-time which is curved and quickly evolving in time. We don't have a quantum field theory in such a space-time. So all computations, in fact, neglect the time evolution. So the inflationary concept appeared in almost more than 40 years ago, 1981. The first model was quickly rejected as false, and up to now there is no standard model for inflation. We have standard model for cosmology, which is extended due to new observation. We have standard model in particles, which is extended in different directions to meet future observations, but there is no standard model in inflationary scenario. There's great variety of models. They form something like a sequence, but this sequence is divergent. So it depends on the author which model he accepts. You can meet authors which claim that it is sure, absolutely sure, that inflation did occur, and some authors which claim that it is just imagination. Most of cosmologists seem to believe in inflation, so we must take it into account. Well, then next very important epoch is electroweak epoch, which lasted from 10 to minus 32 to 10 to minus 12. Again, these two, beginning and its end, are model dependent. This is the period of evolution when well-known physical theories apply, so like general relativity, QCD, and electroweak theory. We assume that either at the end of inflationary epoch or the beginning of this electroweak epoch, the inflaton disappeared and generated secondary matter. This newly created matter consisted of quarks, leptons, and their bosons. And these particles, because it was very dense, these particles interacted very intensively, and these intensive interactions, as usual, lead to lead to thermalization of plasma, and this thermalization took place, and it is computed that this thermalization in the state of thermodynamic equilibrium was reached about 10 to minus 22 seconds. And this was the so-called reheating, and the plasma got a typical temperature about 10 to 14 GeV. Well, so from now on, the plasma expands with space, gets diluted, and gets and it cools down, remaining in the equilibrium. At that time, the universe was the simplest possible, much simpler than the universe today. Now, at the end of this electroweak epoch, 10 to minus 12 seconds, typical temperature about 100 GeV, we expect there was third phase transition, so-called electroweak phase transition. Years of computation, it was estimated that it took place at temperature about 160 GeV. It was so-called electroweak symmetry breaking, and it had two consequences, namely, first, there were the Higgs mechanism, very strange and counterintuitive mechanism which caused that almost all particles acquired their rest mass. Earlier they were massless. And the second, what is important, that this electroweak interaction was broken into forces with different properties. This electromagnetic interaction carried by photon, and weak nuclear force carried by bosons W plus minus and Z0. Well, so what we can say. Next epoch is quark epoch, which lasted from 10 to minus 12 to 10 to minus 5. Well, but this is just to mention that quark epoch is rather less interesting for us. Now we come to the main question: when and how did the baryogenesis occur? The answer is simple: we do not know. We do not know because there is a variety of concepts. It turns out that any real description will be very, very complicated. There's no simple problem. There's no simple model. These are very complicated situations. There are two leading groups. First, baryogenesis occurred in grand unified theories. The other one is that it occurred at the end of electroweak epoch due to this electroweak phase transition. The first concept that we should describe baryogenesis in terms of grand unified theories is easy to apply. Easy to apply because in this theory it is easy to change baryons into leptons and vice versa. So one gets the baryon number violation very simple. The problem is that how to put it in the early universe according to this chronology which I showed you few minutes ago, the inflation occurs after the grand unification epoch, when these good theories worked. And it is clear that this baryon asymmetry must have been created after the inflation. Whatever occurred before inflation, then it disappeared due to expansion. So all properties of the universe, including the baryon asymmetry, must have been created after the inflation. While here we see that inflation was after this big progress. So the simple concept that we use, grand unification theories, is excluded. But we can make some maneuvers with these epochs, because they are very strongly model dependent. So we can have inflation in grand unified epoch. Then we have, and then these theories still are valid when the baryogenesis was created. This is very, very complicated model. And of course, I say that these unified theories are very copious, but most of them is in some way excluded by other effects. So we have mainly negative information, not positive. We don't know what is true, but we know what is false. So in goods it is possible to have generational baryons, but it is rather hard. The second idea is that we have electronic baryogenesis, which it is maybe called a sophisticated non-equilibrium process, because this thermodynamic equilibrium must be broken, that is this process, and it occurred during this electronic phase transition, just at 10 to minus 12 seconds at temperatures below this critical temperature 160 GeV. The problem is in this case that this transition to produce baryogenesis must be, as it is called in statistical physics, must be of first order. First order phase transition is just the condensation of vapor into water. There are smoother phase transitions, second order and higher. And in standard model, this transition is smooth, so the baryogenesis is excluded. So one must use some extensions of standard model, and which one we don't know because most of these models are excluded. So, conclusion is that baryogenesis took place in a very early universe, and we reliably know almost nothing about how it occurred, what was the physical mechanism of baryogenesis, and when it was occurred. So this is just to sum up, it is that baryogenesis is one of the fundamental problems or mysteries of modern cosmology. Why there is matter rather than matter? Thank you very much.
Thank you very much. It was very inspiring, in spite of no answer to the first questions. And now questions from the audience. Starting from the upper row.
Thank you for the lecture. So I'm not a specialist in cosmology, so I have two questions. First, it's why when we spoke about Big Bang, we say about three-dimensional. It's three space-dimensional, and how we add time to our equation if time does not exist at this time.
Well, the Big Bang is an astronomical name for this initial singularity. Singularity means that curvature singularity in the simplest version, which here is valid, assumes that we have three-dimensional space. So in this sense, in mathematical, we have different points, and they are identified by three numbers. So this is three-dimensional. But all distances between different points are equal to 0. There's a very simple model. You imagine a plane, which you have the lattice of Cartesian coordinates, and this plane is expanded. You take a circle very far from the origin, and this plane is isotropically expanded. So this lattice or this Cartesian lattice expands. If you look at the opposite side, this plane shrinks to a point. Still, in this case, it is two-dimensional, but all points of the plane are metrically shrunk to 1 point. So in this sense, we usually say that the singularity is a point in this metric sense, but in fact mathematically it is a three-dimensional set of points. Well, and you had a second question.
Yeah, please correct me if I'm wrong, but how we describe the matter in the first stage, if we know that the matter obtain a mass by Higgs mechanism by a later stage of our universe?
Yeah, it is a good question, but very difficult to answer. Because it is constructed in quantum field theory, it is first assumed that we have these particles of the standard model, which we know 6 quarks, 6 leptons, and all these particles are exactly massless, so the mass is not their constitutive characteristic, and there are furthermore so-called Higgs fields. The simplest model is of one field. Now it is known that there must be a number of fields. They interact with this matter, and at some temperature of this plasma, because these particles form a plasma, at some temperature of this plasma, there is a phase transition. It's the term taken from statistical physics, but it is because due to mathematical similarity, but we cannot assume that it is. Well, perhaps we can say that it is something like condensation of vapor into water, that these Higgs fields interacting with all particles give them mass. It is mathematical procedure which is now commonly accepted. It is believed that it occurs, but there's no intuitive how to describe it. All these things are described in purely mathematical, theoretical concept. It is very far from our intuition, which was, of course, formed on everyday physics.
Thank you.
Next questions.
Going back to the inflationary epoch period, can you just again stress how the quantum chromodynamics and Weinberg-Salam model gave rise to inflationary energy, and then how this energy term then decays. You said that basically we don't know how the inflationary energy decayed into the matter we observe today, but can you just suggest what could be the causes for this?
If I understand your question, you ask what is the relationship between inflationary evolution, the inflaton field, and electroweak theory. Is it so?
Yes.
Yeah. The answer is this relationship is rather loose, because to have inflation we must have inflaton field. Historically it was good in 1981, tried to make this inflation very physical, and he assumed that it was this Higgs field, but very quickly turned out that it was false, and we must assume that there was a special inflaton field in fact just to provide inflation when it disappeared. So this field has no explanation, there's no need in the standard particle model. So it is completely different. Now, of course, this model, because we know, we just introduce this field just to have the inflation. It's clear that we can give it arbitrary properties. So usually it is claimed that it is scalar field, because it is simpler, the computation in this case is simplest, but you can assume, I saw papers where it was claimed that it is a vector field, or it is a collection of scalar fields, so it may be arbitrarily complicated, just to obtain something that would be consistent. And up to now, we don't have it.
Thank you. Any more questions? Oh, yes.
Thank you for an interesting lecture. I have one question about connection between gravitational waves and inflation. As you said, there is no standard model of inflation inflation itself. If we could detect the primordial gravitational waves, could we set a standard model for inflation, or?
I don't have a definite answer to this question, because first, gravitational waves may be produced in astrophysics in many situations. This is the generic problem of astrophysics. We observe some signal, electromagnetic or even gravitational, and we try to guess what was the mechanism producing. And there is a number of because we do not control the process of the emission of the gravitational waves. So usually there is a number of possible sources, and we try to eliminate most of them to have one source. In the case of inflation, because we have first, all this, as far as I understand, because I'm not an expert in inflation, I belong to these people who claim that it is a false idea. And I'm not a physicist. As far as I understand, then in inflationary models, there is none of these models, there is no detailed description of the phase of decaying this field. Because you can obtain, very simply, you can obtain this field which has a constant energy, inflation goes on, but then you would have no universe as it is. You could have very quickly expanding universe, which would be perfectly empty of everything. So in this sense, we must assume by hand something which causes that this field decays. There are some computations because it cannot be a completely homogeneous process. There might be in one part of space it goes faster, in other it goes slower. So there are some perturbations, and these perturbations in density of created particles may produce gravitational waves. But all computations are simplified, and moreover, all these waves may be, if we see some gravitational waves, usually we can explain them in a simpler way. Simpler in the sense that the source is closer to us in time.
So may I suggest that the discussion continues at the coffee break, because we should be back here at 11:30 for the next lecture, then 20 minutes of coffee break and